Okay, so you have just completed an experiment at home, hopefully, where you took some kind of rigid object, a ruler, a book, a cell phone, a calculator, a piece of wood, something, and you propped it up against a wall and a table, or a wall and the floor, or something. Carpet, hopefully not, because carpet doesn't work as well, but maybe you did. But carpet's going to exert some extra normal force here, which we don't want. Okay, and what you hopefully found was that this angle theta, as you varied that angle theta between the object, the rigid object, and the floor, I'll just call this the floor, you found that as you changed that angle, as you made that angle smaller, suddenly you hit a point where this rigid object just starts to slide down the wall. And this end slides out that way, and this thing falls to the ground. So there was some point, like some minimum distance out this way, sorry, some maximum distance out this way that you could put this thing, or some minimum angle you could have this at, and then any angle smaller than that, I keep saying minimum when I mean maximum, any angle smaller than that, this thing would just tip and fall. Okay, now why is that? Well, I asked you to do some thinking about that too. I asked you to draw some free body diagrams. I asked you to look at the torques exerted on this thing, and hopefully you looked at it and said, well, it's the forces acting on it. What they are isn't changing. How large they are is changing, and how much torque they exert is changing. And so the increase or decrease in the size of some forces, plus the amount of torque being exerted by those forces, are what take us from a situation like this, where we're going to call it a stable equilibrium, a situation where this thing is in equilibrium. It's not going to slide, so it's not going to have any linear acceleration, and it's not going to rotate, so it's not going to have any angular acceleration, to a situation like this, where this object is both sliding and it's rotating, because the angle it makes with the ground is changing. So equilibrium, if I was thinking about the things I want you to get out of this lesson, equilibrium, one of the big things, or is one of the big ideas. Equilibrium means that this object has net torque equals 0 and net force equals 0. So maybe I'll just write that up here. That equilibrium for us, and it's called, I guess, a static equilibrium, means that net force acting on some object, some rigid object, is equal to 0, and net torque, which is normally equal to I alpha, we want that to equal 0. So this thing's not accelerating sideways and it's not rotating. Okay, well, what's going to control if this thing slides or rotates, or if it doesn't do those things? Well, it's going to be all about the forces acting on this and the torques acting on this. So the sample problem we want to solve, we want to say, given these things, given that I have some bar that's mass is m, and I have a bar that has a length L, and I'm going to define the angle that I'm trying to prop this up at. I'm going to define that angle as some theta 0. So the angle theta 0 is a fixed angle. We're not letting this thing rotate in this example. Okay. Given that fixed angle, what coefficient of friction do I need? What mu do I need right here? Mu with the floor. Okay, so that's going to be our sample problem that we're trying to solve. I have a feeling this might take 2 videos to get through, but because I'm already 3 minutes in, but we'll see. All right, so if I'm in equilibrium, if I want this thing to stay at rest so that it's not going to slide and it's not going to rotate, then I need to meet these 2 conditions. Well, in order to meet these 2 conditions, I probably ought to look at, well, what forces are actually acting on this thing, what torques are acting on this thing. So I'm going to focus just on this picture. This picture now, this lower picture, we can pretty much ignore that for this point until the end when we talk about, well, what happens to these forces later. All right, so the first thing we want to do is start to talk about what forces are acting on this. So let's take some of the easy ones. Gravity is definitely acting on this bar. Okay, I just called it a bar because it seemed like a good name for a rigid object. There's the center of mass of that rigid bar. Where do we act like gravity acts on this thing? Well, gravity applies a force to each little piece of mass all along here, but gravity behaves and applies its force as though it's acting at the center of mass of this object. Or maybe I should say that not the gravity behaves that way so much as the object will behave. It will move as though gravity is being applied at the center of mass of that object. Okay, so that's our first force. All right, next thing we have acting on this. Well, you have this bar pressing against the ground. Well, then the ground's probably pressing back against the object. So there is a normal force. Now, what direction does that act? Well, it always acts perpendicular to the surface. So the normal force is going to act up this way. I drew that arrow a little big. It's really not drawn to scale, but just pretend that it is. Okay. I also have another force. I have the force that the wall exerts on this thing. So let's draw that in red. Okay, so I have the force that the wall exerts, because if I think about it, if I took that wall away, what would happen? This whole thing would fall that way. So the wall clearly has to be exerting some force there. Just like if I took the floor away, what would happen? Well, this would all fall down. So the floor has to be exerting a vertical force. Okay. At this point then, there's always the debate of, well, is there friction or is there not friction against the wall? There is friction against the wall. For this very first example that we're going to do, I'm gonna cheat and I'm gonna say that this is frictionless, just because this is our very first example. Okay, but you could solve it if there was friction, and we'll do that at some point. I'm just not going to do it now. Okay, so we're going to ignore the friction with the wall. All right, do we have any other forces? Well, if I want this thing to be in equilibrium, there has to be at least one more force. How do I know that? Well, because I have gravity and normal force. Those two could be balancing each other vertically to meet this condition, that net force equals ma vertically. But right now I have an unbalanced horizontal force. Okay, so if that force remains unbalanced, this whole this whole bar should start accelerating that way. Well, what's going to hold it in place then? Probably you have to have some friction. So friction needs to oppose that force of the wall, so I'm going to have a force of friction down here. And it'll be, we'll say static friction for now, but because we want it to be in equilibrium, but it doesn't, that's just what we'll say for now. Okay, that seems like that could be enough for us. Now some of you may be arguing, well, is there a normal force exerted up by the wall? Nope. Remember, normal forces always act perpendicular to the surface, so there's no normal force there. What else? And again, we already eliminated that friction, so we're good there. All right, so then we're going to move on to the net force side of this, and we want to look at the net force horizontally. Okay, we need to look at the net force vertically. Okay. So horizontally, I'm going to have that, let's see, I'm going to have net force is equal to ma, and I want that to equal 0. So I'll have that the force that the wall exerts minus the force of friction has to equal 0. So that means the force of the wall has to equal the force of friction. Now, hidden in force of friction, I have that mu that I'm actually looking for, so I might as well put that in there. So I'll say that the force of the wall equals mu times normal force. Okay. I don't know how big that force of the wall is at this point. Otherwise, I'd be good to go, because I think I can find normal force. We'll try that out. All right, on the vertical side, I'll do the same thing. I'll say net force equals ma. And again, if I'm looking at equilibrium, I want that to equal 0 too. Equilibrium says no unbalanced forces in any direction. Okay, so vertically I've got gravity acting down, and that's going to equal the normal force acting upwards. Okay, so now I know how big normal force is. So I can plug in and say that the force of the wall is equal to mu times that normal force, which is just mg. This is fine. I'm given mass of the bar. I'm allowed to just use that as m, so that's fine. G is fine, but I don't know how big this force of the wall is. So I can't just say, oh, mu equals whatever. I can say force of the wall divided by gravity is equal to mu, but I still need a way to find mu. Or, sorry, find force of the wall. Where am I going to get that? Well, fortunately, I've taken care of this condition for static equilibrium, but I have not taken care of this one. So let's talk about that situation. And I'm going to pause the video there. Well, no, I'll see if I can finish it. All right, so for that one, I'll say that torque net needs to equal I alpha. All right, and I need to always sum my torques around some location. Well, there's several locations that make sense. The idea is that you would pick a location that would eliminate some of the torques. So if I pick this base, then normal force doesn't exert a torque and friction doesn't exert a torque because there's no radius, so there's no lever arm. If I pick the center of mass, that's good because that eliminates gravity. Then I have these two, and the wall exerting torques. And if I pick this point, that's a decent point too, because then I eliminate the force of the wall. I can pick any of those points. It seems like this base point, so I'll call it B for base. This B, this location seems like the best choice because it eliminates two forces from the torque equation, because now this isn't going to exert any torque around that point, and this isn't going to exert any torque around that point. So I'm going to sum the torques around point B, which means I need the rotational inertia around point B. Alright, now this video is starting to get long, so I'm going to stop it and just restart in a second.